We have already done it. So imagine I have the change of transformation xi of uk, where I is 1, 2, 3 n and k is also 1, 2, 3 n. So it's like x is x of u1, u2, u3 and un, and y x2 is x2 of u1, u2, u3 and un, so on and so forth. Okay. And imagine I have an abstract line element. So how does that abstract line element is going to look like in these new coordinates actually? So I know that the line element can be described by metric tensor. Okay. So it's like Gij, okay, multiplied by dui square. Now if you have orthogonal transformation, the other g, when g and I are, so if you have an orthonormal frame, okay, normal frame, then I know that Gij, okay, is going to be what? What is Gij actually? What was Gij? So you just have to compute the inner product of partial I and partial j actually. Okay? So that was our previous description, but I can now also describe them in the terms of the new coordinates, so ei, ej. So this would be nothing but delta ij, or maybe delta ij. Are you getting the point? So if this is delta ij, that means that the only G11, G22 and G33 will survive. Okay? So if I have an abstract system, it's going to be Gij, Dui, Duj basically. This would be the abstract description of it. Abstract description of line element. But if I'm in an orthonormal frame, this is going to look like ds square. So it's going to be G11, okay, du1 square, G22, du2 square, and G33, du3 square. Okay? So give me theta 1, theta 2 and theta 3 in this case. So just get a motivation what we did in cylindrical coordinates and tell me what would be theta 1, theta 2 and theta 3 here actually.
du1. du1
So it must be square root of G11, okay, du1, isn't it? Okay. And theta 2 would be square root of G22, du2, and theta 3 would be square root of G33, du3. Okay? For the sake of simplicity, I am defining Hi to be the square root of Gii. Okay? So each of the theta I would be Hi
dui.
So this would be where I is 1 to 3. I is 1 to 3. So this is what I am defining at. These are what do you call the scaling factors. Alright. Now, what I want theta i's to be, I want theta i's. So theta i's are what? These are my co-frames actually. So I want the theta i's to be orthonormal to the basis actually. So theta I of Ej I must want to be them to satisfy this condition actually. So this is my wish. Okay? This is my wish. So if I have description of theta i's, the question is what would be the description of Ej? In other words, what would be even? In other words, what even I must write so that when I apply theta 1 onto the even, I must get 1. And if I apply theta 1 onto the E2, I must get 0. And theta 3 onto the E1, I must get 0 actually. So the question is, what should be my even? Have a guess. What should be even? So 1 by G11 Hi and partial by partial U1. Think about it. 1 over H1 and partial by U1. And think about it. So now if I take theta 1 and I operate it onto E1, what I'm going to get? So I'm going to get H1, okay, H1 multiplied by 1 over H1 last one. 1 over H1 and E1 operated onto partial by partial U1. So it's going to be delta 1 1 actually. Okay. So you're going to get, so this will be delta 1 1 and hence you get a 1. Okay. And similarly, if you apply theta 2 onto E1, you're going to get what? You're going to get, okay, H1 1 over H2, but this will be delta 1 2 actually. And hence you get the thing. Are you getting the point? So hence, the abstract description of EIs must be 1 over, maybe Ej must be 1 over Hj and partial by partial Uj. Is it making sense? So why this is a very powerful formula? Think about it. Think about it. And why metric tensor is a very important quantity. So imagine you only know the metric tensor. In other words, you know that how the space is transforming basically, like through the ideas. So I can compute the co-frames. So these are abstracts. You just need HIs. And HIs are what? They are, the square root of GIIs. I can compute frames actually. So just take the reciprocal of it. Are you getting the point? So you will see afterwards that if you know the metric tensor for a given space, okay, then you can compute all kind of the gradient, divergence and all these quantities actually, specifically in Euclidean space. Is it making sense? Okay. So let's think about gradient. Let's think about the gradient. How does the gradient would look like using these notations? Okay, so what would be the df? So if f is, a scalar field described in the terms of u1, u2, for example, u3, depending on. As previously it was r theta z, so now you have this u1, u2, u3. Okay? Then what would be df?
Partial f by partial u1.
So it's going to be partial f by partial ui and u. making sense? And if I want to have a correct expression of df, then I need to do what? I need to express this in the terms of the thetas actually. So how can I turn this expression in the terms of? Doing something stupid. Okay, so alright, I can do directly this, but you can ask the question that how did I reach to this point actually? So I can do this, that okay, so for example partial f by partial xk and dxk, and then I can write this partial f by partial xk. So it's like in order to compute this partial f by partial xk, I have to apply chain rule. And that chain rule would be a sum actually. So partial f by partial what? ui and partial ui by partial xk and dxk. So this is a sum actually. So each of these partial f by partial xk computed through this expression. This is a sum in I. Multiplied by dxk. And this is what? This is nothing but dui actually. Okay? So what would be the dui's? The dui's are going to be partial ui by partial xk, dxk actually. So we expressed df in the terms of dui's. Okay? So if I want to express this in the terms of theta, what I need to do?
1 over hi theta.
So I have to do 1 over hi. Okay. I have to be now a bit more careful because I have to repeat an index 3 times. Okay. Then you have to explicitly say that you are summing up over I actually. So you can't just write, you can think about it. So what would be dui? So it's going to be 1 over hi theta I. But in this case, you're going to get partial ui and 1 over hi and theta I. But you're going to say that using Einstein summation convention, this doesn't make any sense actually. Because the index cannot repeat more than 2 times. So you have to tell explicitly that I am taking a sum actually over I. Okay? So this would be the description in the terms of this. Hence, what would be the gradient in so what would be the gradient in so purely in the terms of these coordinates is going to be this object. Okay. This object. So you don't need to give reference to the theta i's actually. Like as we did in case of loss operator or maybe the differential in previous cases, symmetrical coordinates. So this would be what do you call the differential of the f. Is it making sense? Okay. That will be the gradient of f. So if I write it more explicitly, it would be like that. So what would be gradient operator? So the gradient operator is a vector in which each of them is this component actually. So 1 over h1 partial by partial u1, 1 over h2 partial by partial u2 and 1 over h3 and partial by partial u3. So that's a gradient operator. Curvilinear coordinate system. Is it making sense? So you see, what is the power of this formula is that if you know how the space is curving, In other words, you know the metric tensor, you can directly compute the gradient in it. You can directly compute the gradient in that formula. Just put h1, h2, h3 there, and you are done. Okay, still have 5 minutes, so I'll just calculate one part and leave the other two, obviously.
सर फिर सम को तो हम डाइवर्जेंस कह सकते हैं ना.
What do you mean by that?
ग्रेडियंट नहीं कह सकते. ग्रेडियंट हमारा वेक्टर होता है. तो सम को हम नहीं कह सकते ना ग्रेडियंट.
So it's like I can say that an operator is operating on the theta I भी है ना.
वो मतलब
ठीक है. Anyways, you got that.
Oh, this is it.
Yes. So it's like, this is like a vector. Vector shouldn't be a vector, but okay, it's somehow roughly like a vector. So what would be curl? So I know that for curl, I must have a vector field f1, f2, f3, and in form I need to write it as f1 theta 1 plus f2 theta 2 and f3 theta 3. Okay, and if I write it in the terms of u coordinates, I need to describe theta 1, theta 2, theta 3 in the terms of u's actually. So it's going to be h1 f1 du1.
No, sir. 1 over h.
मैं बताइए थीटा 1 कर दे.
Theta 1.
या तो प्लस
Same.
Okay. You get h2 f2
Theta.
du2 h3 du3. Okay, so this is a complete description of. By the way, what was the expression for the curl? So if you want to compute the expression of the, so if you want to compute the curl in
Sir, it was exterior derivative of alpha and then operated this operator.
O star of D.
so that's your alpha. So operated D on it. So this would be the curl. So operate an exterior derivative on it and then compute the star of it. So what would be the exterior derivative of f actually? So if you have to compute the exterior derivative, you have to do what?
Two form में करना पड़ेगा.
Okay, it's gonna be in two form, converted in two form. So you have to do this. Okay. So you're gonna get this. So we have computed it basically. So what was, okay, so I'm just directly writing. So it's gonna be 1 over 2. Okay, 1 over 2. So just recall the expression when we treated D onto a one form. So it's going to be 1 over 2, okay, partial. Should I write one step again? So if I say hi, okay, hi, maybe hf, and I have an ith component basically of f and multiplied by d1. What are we going to carry on?